Hello friends, in this video I'd like to solve this very standard number theoretic problem from the Thailand Mathematical Olympiad 2004, problem number 13. We wish to compute the remainder upon division of 29 to the power of 30 plus 31 to the power 28 plus 28 factorial times 30 factorial, division by 29 times 31. My hints for this problem: Wilson's theorem will be useful. Wilson's theorem states that if p is a prime number, then p minus 1 factorial is always congruent to minus 1 modulo p. Fermat's little theorem may be useful. If p is a prime, a is an integer not divisible by p, then a to the power p minus 1 is always congruent to 1 modulo p. And also, it may be useful to use the Chinese remainder theorem. So our problem is equivalent to finding our remainder upon division by 29 and 31 separately, and then combine them using the Chinese remainder theorem. We'll give this problem a try, and I will see you in a minute. Okay, so my solution, let's notice, first of all, let's notice that both 29 and 31 are in fact primes. And now we'll consider separately our expression modulo 29 and separately modulo 31. Okay, so we have the following. This expression is congruent to what? Well, 29 is congruent to 0, modulo 29. 31 is congruent to 2 to the power 28. And finally, let's notice that in 30 factorial, this number is 28 factorial times 29 times 30, and 29 appears in the factorization, so that's also congruent to 0. And now by Fermat's little theorem, 2 to the power 28 is congruent to 1. Yes, 2 to the power p minus 1 is congruent to 1 modulo p if p is odd. It's by Fermat's little theorem, modulo 29. Okay, so now we know something. We know that our expression is congruent to 1 modulo 29. What about modulo 31? Let's look. It will be probably harder. Let's look. Our expression is congruent to, well, 29 is congruent to minus 2 modulo 31. 31, it's obviously congruent to 0. And here, finally, we have 28 factorial times 30 factorial. And let's leave it in this form for now. And now let's consider this, and that separately. What do we get? Well, minus 2 to the power of 30, again, by Fermat's little theorem, it's just congruent to 1 modulo 31 by Fermat's little theorem. Okay. What is 30 factorial congruent to? Well, it's 1 less than 31, so it's congruent to minus 1 by Wilson's theorem. And finally, what is 28 factorial congruent to? Well, Well. Let's see. Let's say that it is congruent to x, modulo 31, and we can do the trick. What trick? We can multiply both sides of our congruence times 29 and times 30. We can do it because 29 and 30 are co-prime with 31. So we will get the following. Here we will get 30 factorial is congruent to 29 times 30 times x modulo 31. And now we know that 30 factorial is congruent to minus 1. 29 is congruent to minus 2. 30 is congruent to minus 1. And now let's do one more trick. I will add only to the left hand side 31. I can do it because 31 is congruent to 0. And I get 30 is congruent to 2 times x modulo 31. And now I divide by 2. It's legal because 2 is also co-prime with 31. And I get that 15 is congruent to x modulo 31. Okay. So we have 15 minus 1, 1. So let's go back and let's write it here that this is congruent to 1 plus minus 1 times 15. Or you know what, now we don't have space, so it's write it here. This number is congruent to minus 1 to the 30 is 1, 0 is 0, 28 factorial is congruent to 15, 30 factorial is congruent to minus 1. So we have minus 14, and minus 14, let's convert it to a positive number. We can add 31, and we will get 17 modulo 31, sorry. Okay, so let's group these results together. We now know that our number is congruent to 17 modulo 31, and it was congruent to 1 modulo 29. Okay, and you know what, I'm getting tired of writing all of that. Let's say that this number is A is congruent to this, and A is congruent to that. And we have now to solve this system of congruences. We have to solve it. Or we have to guess our answer, but let's not do it. So first, our first equation, so it's asterisk, it's double asterisk. From single asterisk, we get the following, that A equals 29k plus 1 for some integer k. And let's put it into our second equation. So maybe just double asterisk says now that 29k plus 1 is congruent to 17 modulo 31. 29 is congruent to minus 2, so we have minus 2k is congruent to 16 modulo 31. So k is congruent to minus 8 modulo 31. Okay, so k is congruent to, we can add 31, it's congruent to 23 modulo 31. And I run out of space, and I have to add a new page, and I will do it. Why not? Okay, so now we know that A equals 29 times 23 plus 31 times L plus 1, where for some L, which is integer. Oh no, now comes the hard part, namely computing large numbers. I hate this part. I hate it so much. 23 times 29 plus 1 plus 29 times 31 times L. And let's multiply it. Give me a moment. I have to use a calculator. 23 times 29 is 667 plus 1. 668 plus 29 times 31L. And that means, remember that we want to find the remainder upon division by this number. So it's just 668. So this number modulo 29 times 31 equals 668. And that is our answer. Okay, so thank you for watching. I hope that you've learned something new. So as you see, very standard problem, Wilson's theorem, Fermat's theorem, the Chinese remainder theorem, and that's all. Thank you for watching, and I will see you soon. Goodbye.